In this chapter, chapter 4, we're going to talk about global climates and biomes. So your book always opens with a case study, and the first one was talking about a case study in Kenya. In April of 2003, there were very heavy rains. There was flooded villages, and it really devastated western Kenya. Whereas in northern Kenya, there was drought resulting from the lack of summer rain, and there was no rains there until 2006. What happened? Global processes, which we're going to look at, really drive rainfall patterns. It's not really understood why the rain clouds didn't move that year, but it's had a huge impact on Kenya. People had to walk hours for water. I've spent some time in Kenya, and I'll kind of take some class time to share with you my experiences when I was there. But the water situation is devastating and fascinating for those of us that live in a first world country and don't have to think about water as a basic human need. So global processes determine weather and climate. We need to know the difference between weather and climate. Weather is our temperature, humidity, clouds, precipitation. Is it going to rain? What clothes am I going to wear tomorrow? Is it going to be 70 degrees? Is it going to be 50 degrees? We can predict the weather more than a few days. That's sort of it. Climate is the average weather that occurs in a given region over a long, typically decades period of time. And people sort of say, oh, there's a hot day in December and that's climate change. That's not climate change, that one single anomaly day. Climate change has to be looked at over decades. So we always have had different days that are, too cold or too hot. And that's just weather. That's not climate. Looking at our atmosphere, there's 5 layers of gases. The troposphere, which is the layer closest to the surface, about 16 kilometers above the Earth. That's where our weather takes place. The stratosphere, which is above the troposphere, is about 16 to 50 kilometers. That's where our ozone layer is, and the ozone layer is going to be very important to regulating the surface temperature of the Earth. We'll delve into that more deeply when we get into greenhouse gases. The mesosphere, the temperature decreases with altitude. Thermosphere is what helps to block harmful X-ray and UV radiation, and that's where, if we have auroras, that's where those are going to take. And our exosphere is our outermost layer of the atmosphere. So part of what drives our climate is the unequal heating of the Earth. So as the sun's energy passes through the atmosphere and strikes the land and water, it unequally warms the surface of the Earth. And that has to do with the angle at which the sun's rays strike. There's a more direct strike at the equators and less direct strike over the poles. And there's also certain areas of the Earth reflect more solar energy, so that albedo effect comes into play. So if we look at this diagram here, we can see that the sunlight strikes the Earth here. Oops, sorry about that. And it's very perpendicular, okay? So this solar energy is very, very direct at the equator, okay? Here we have much more of an oblique angle, and it has to pass through more of the atmosphere, and it loses a lot more of its energy than it does at the tropics, okay? So this is a big contributor as to why we have unequal heating, just due to the shape of the Earth. Okay, the amount of surface area over which the sun's rays are distributed. So when the sun is hitting the equator, this amount of sun is being distributed over a smaller area of land, which means more of that heat is being transferred there. And here the sun's rays are spread over a wide area, and the same thing is true here. The sun's rays are spread over a wide area. We also have unequal heating of the Earth due to albedo, okay? So this is that reflection of the sunlight back up into the atmosphere, okay? So the average is about 30%. Water, depending on the sun's angle, can be from 10 to 60%, okay? So you guys know that when you're at the beach and you're also skiing, both of those things have a high albedo, and that's why you have to wear sunscreen. So this light comes in and gets reflected back up onto your skin. And the same thing is true for fresh snow. That's why you end up getting sunburned when you go skiing, because that's reflecting that light back in there. Whereas if we look at other areas like forest and grasslands and those kinds of things, they have much less albedo. A lot less sunlight is reflected in the forest or in a grassland. Asphalt also absorbs much more because of its dark color. Okay, so we have this bright white color, we have this reflection of the sea ice in the sun. So looking at currents, air has 4 properties that determine its movement. Density, so less dense air rises, denser air will sink. Okay, that sort of makes sense. We get that idea of density. Water vapor capacity. Warm air has a higher capacity for water vapor than cold air, so it can hold more moisture. And that has a saturation point. Abiotic cooling, air rises in the atmosphere, the pressure decreases and the air volume increases, and expansion lowers the temperature of the air. And then latent heat release, when water vapor in the atmosphere condenses into liquid water and the energy is released. Okay, so if we're looking at those properties, we're going to end up with some convection currents. Okay, and so this is this idea where these Hadley cells meet up, and that's we talk about this mostly at the tropics. So at this ITCZ, the intertropical convergence zone, the sun heats the moist tropical air, causing it to rise. It rises up here. The rising air experiences this abiotic cooling, which causes water vapor to condense back into rain and fall back into earth. So this is, this is our hot, moist tropics are here. The condensation of the water vapor produces latent heat release. This causes the air to expand and rise further up into the atmosphere. The warm rising air displaces the cooler, drier air above it to the north and the south, so it's kicking this cooler, drier air this direction and this direction. The cool, dry air sinks, experiences abiotic heating. Okay, so it's back down here where this hot, dry desert is. It's going to get heated up again. It's going to flow back towards the equator. It's going to pick up more of that moisture, and it's going to continue on and on again. This is why we have so much moisture at the tropics. This is where those Hadley cells really meet up, and the convection currents that cycle between the equator are the ones that we really talk about, but then also at 30 degrees north and south of the equator. Okay, so if we look here, we can see these Hadley cells and where they meet, and this is this intertropical convergence zone. This is where this is all meeting, and that's why we have so much moisture right along the equator here. It gets the most intense sunlight, so it's going to have the most intense Hadley cells. It's going to have that process that I just described occur most intensely. We have the same thing here, where these Hadley cells meet at 30 degrees north and 30 degrees south, and it just doesn't, even though we sort of switch directions in the polar area, it doesn't form that distinct convection shell. There's not enough differentiation in temperature for that really to occur. And now we're going to take a look at the Coriolis effect. So now we're going to take a look at the Coriolis effect. So Earth's rotation has important influence on climate. This is like the video we watched where if you're standing in Texas and you throw a paper airplane, you would think it would head due north, but it's actually going to sort of curve off towards Delaware. And there's a couple good videos on the Coriolis effect, if you missed them in class, linked to my website, so you can take a look at them. But this is that idea, and we did the simulation, the merry-go-round idea, which is this, where if you were to have two people and they were to throw a ball at each other, you would think that they'd be able to catch it, but if because of the Earth is rotating, the ball is going to appear to curve off. Okay? So Earth's rotation, the Coriolis effect, this is what's influencing these prevailing winds. So they're produced by a combination of atmospheric convection currents. So we have these Hadley cells that are meeting, whatever, and we also have this Coriolis effect. Okay, so we have both of these things, that are joining in to change the way our winds flow. Okay, so we know that in the northern hemisphere we have one direction of rotation, whereas in the southern hemisphere we have the opposite direction of rotation. And then this is really magnified along this intertropical convergence zone. And so this is just putting all of those ideas together. We have this deflection due to the Coriolis effect. We have these Hadley cells meeting up, and this is what's going to make our northeast trade winds and our southeast trade winds. And this is going to come into play when we start looking at the El Nino effect. Okay, so look at this direction that all these winds are pointing. Okay, that's going to be a key piece coming up. We know the Earth's tilt fits into the seasons, so the Earth's axis is tilted at 23.5 degrees. It causes most regions to experience seasonal change, some more dramatic than others. But it has to do with when that part of the Earth is tilted closer to the Earth. So that degree, that 23.5 degrees, is enough of a tilt that it influences the temperatures on the Earth. Okay, so we're pretty familiar with that idea because we live in an area that experiences seasons, and it has to do with when we are tilted towards the sun and when we are tilted away from the sun, as opposed to our actual distance from the sun. Looking at ocean currents are driven by a combination of temperature, gravity, these prevailing winds, and the Coriolis effect. All of these things come into play in location of the continents. We have a lot of things that are influencing our ocean currents. So it's not just a cut and dry, this is why this happens. There's all these things that can impact both our climate and our currents and our air. Warm water, like warm air, expands and rises. And gyres are the large-scale patterns of water circulation. It redistributes heat in the ocean. Upwelling, this is this idea as surface currents separate from one another, deeper waters rise and replace the water that has moved away. So if we look, we have some big, complicated oceanic circulation that goes on. And part of this is, the continents get in the way of this, and you can see these big upwelling zones. These are big areas where lots of nutrients come up from the bottom. As this warm air is displaced, this cooler water, cooler water upwells. Okay, so as this warm water is replaced, and it makes sort of a global current pattern, circulation pattern. Thermohaline circulation this is oceanic circulation, which drives the mixing of surface water and deep water. It takes hundreds of years to complete. It's hard to envision the total quantity of water that's taking place in here, and we know that water has a high heat capacity, so changes in temperature are very slow. There's lots of factors that contribute to this. Ocean currents can affect the temperature of nearby land masses. Okay, so this is important. If our oceanic circulation changes, or our water temperature changes, or our quantity of water changes, because as we have global warming, we're melting more of those polar ice caps, so we're adding more cold, fresh water into that system, we're upsetting the balance, and we don't entirely know how that's all going to play out if we continue on the path that we're on. But this is the overall global circulation. So you saw all the sort of minor circulations. Here you can see this is the big overarching currents that take place in the globe. Okay, so all those smaller currents that we looked at on the couple slides ago combine to make one overarching current. El Nino and the Southern Oscillation, this is the interaction of the Earth's atmosphere and the ocean, which causes surface currents in the tropical Pacific Ocean to reverse direction. This is about every 3 to 7 years, but like we talked about in class, it's not an exact science, and sometimes we don't know that it's happened until sort of after the fact that it's happened. So during most years, we talked about that these trade winds, remember we talked about they're all pushing this direction, pushes and keeps this warm water over here, and this cold, deep water upwells along the coast of South America. In an El Nino year, these trade winds sort of reverse or not as strong, and we don't have this cold water. We have a pool of warm water here, and we've talked about how that's going to impact the global atmospheric conditions, because that warm water isn't where we expect it to be. A La Nina is the opposite. These trade winds strengthen and really push this warm water really far away. Rain shadows is this idea that mountains sort of break up weather as it comes along. So we know that along the coast, but this can come in, and because of this leeward side of the mountain, there comes some abiotic heating and cooling, and it causes the rain to fall on this side, which makes it sort of desert conditions on the other side of a mountain. And that's a perfect place to stop.